My dear students, in the previous lecture, I had introduced to you the solid state chemistry and the crystal defects. This is a very important subject, and as I had said earlier, it provides a lot of commercial products which have marked their way in the business of everybody. Today, continuing with that series, we shall talk of solid state reactions. Now, these reactions are very important to produce any polycrystalline product. They are full of very important chemistry, though very difficult, and number of things that go into their preparations and productions. Accordingly, we shall take up this subject in next few lectures, starting with introduction to the solid state reactions, including general principles, why such reactions are difficult, and their kinetics. Thank you. Then when in the solid state reactions, as per your curriculum, you are exposed to study the following aspects. Number one, general principles of solid state reactions, the experimental procedure. Now, this experimental procedure consists of a number of things which we shall talk later. Then there is a special method of preparing these materials, which is co-precipitation as precursor to solid state reactions. That is, before we go for the solid state reaction, you have another procedure where you get precursors that are to be taken for reaction. They can be co-precipitated and the reaction can proceed. Then we shall talk of kinetics of solid state reactions. In between also we shall talk why these reactions are difficult and how to overcome those difficulties. Now, moving to the solid state reaction methods, it's very important. In the initial stages, I'll go over the general principles or general aspects of these solid state reactions. Thereafter, I shall take up a very specific case of formation of a spindle called magnesium aluminate, and we shall talk of this as a specific case in this study. Now, starting with the general principles and general overview of the solid state reactions, what you see here is that these solid state reactions is a common synthetic method to obtain polycrystalline materials from solid reagents. Now, such reactions are mostly occurred at very high temperature. These temperatures can go as high as 15 degrees centigrade, even up to 2000 degrees centigrade. So therefore, they need some special setup to achieve such high temperatures. Now, these reactions are affected by the reactants' properties, such as chemical and morphological properties of the reagents, which may include reactivity, surface area, free energy change, and other reaction conditions such as temperature, pressure, and the environment of the reaction. These advantages of these solid state reactions are that they include methods which are simple and they allow you to have a large scale production of polycrystalline materials which have very wonderful applications, as we shall see it later. Now, what are the methods that we use and what is the care that must be taken for these methods? There is a diverse list of methods that one can use to synthesize solid compounds and materials. While doing so, one has to take care of few aspects which are very, very important while making these materials. As you would see in this slide, first thing is that the quantities of the reagent to be taken, they must be the stoichiometric quantities. Why we say so? Because at the end of the production, normally there is no purification possible of the product. So therefore, the stoichiometric quantities of the product are to be taken right in the beginning. Second thing is that the purity of the starting material is of fundamental importance. This purity, you can see it as it is indicated here, starts with 99% and goes up to 99.998%. So depending on the material what you are making, what you are intending to make, the purity level of the reagent has to be looked into. Now this purity level is to start to give you a reaction that goes to the completion, and there are no possibilities of any containment in those materials. If you want to make silica glass for fiber optics, the purity of the material, starting material, has to be 99.999999%. Whereas if you wish to make laboratory glasswares, you can have a material with less purity. Then you have to, these materials have unusual oxidation states, such as in the hydrothermal process, and therefore one has to respect these hydrothermal states. The reagents need to be in the powder form and should be in the form of large crystals when you start these preparative methods for making these polycrystalline materials. Moving to the solid state or ceramic method. This is one of the important methods that is used in the preparation of such materials. Now this method consists of heating two non-volatile solids which react to form the required product. The method used for this is to prepare a whole range of material including mixed metal oxides, sulfides, nitrides and aluminosilicates. Example indicated here is zirconium oxide reacting with silica, both are in the solid state, give you the zirconium silicate, and this reaction normally happens at a temperature of around 1300 degrees centigrade. Now this particular method, what is called ceramic method or solid state method, it can be used to prepare extremely large number of compounds. That means this is the general approach to the solid state reactions. The disadvantage of this method, as we have seen the advantage in the previous slide, such reactions are high temperature. Such reactions are high temperatures and generally require a very high temperature, anything between 500 to 2000 degrees centigrade. Why it takes so much of temperature? Because you require energy to overcome the latest energy, so as cations or anions can diffuse into the different state. This much of energy or this much heat is required to provide the required energy for anion and cations to leave their to overcome their latest energy to diffuse into the different sites. The desired compound may be decomposed at high temperature. This is another disadvantage, that you are making a product, but if you decompose at high temperature, then you have to be very careful that not allow this compound to decompose, because otherwise your experiment will fail. Then the reaction may proceed very slowly, and indeed these reactions are very slow, but increasing the temperature, the speed may be increased, as we shall see later in the example. Since why the speed is increased? Because at that stage the diffusion rate increases, that's why the speed of the reaction goes up. Now generally the solids are not raised to their melting points. Now what is the limit of the temperature? Kindly see it here that the solids are not raised to their melting point. So reaction takes place in the solid state or sub-solid state. So therefore there is a limitation to which a particular solid can be heated, and to which one has to take care what temperature it can reach for the reaction to proceed. These reactions, as I said just now, that at high temperature the anion and cations, they diffuse into the reaction site. Now this is a diffusion-based reaction, and this diffusion-based reaction, they follow the Fick's law. There in the Fick's law, Diffusion control, these are the diffusion control reaction. The Fick's law equation is given there with J is equal to minus D dC by dx. Small particle size are well mixed are needed to maximize the surface area contact. So here I am using the word small particles. That means the powder has to be very fine so as to give us a large surface area for the reaction. So that's why small particle size are required to maximize the surface contact area. Then, as I mentioned just now in the previous slide, that up to what temperature you can go. Here is a rule called Taman's rule, which suggests temperature of about 2/3 of the melting point in degree K of lower melting reactant is needed to have reaction to occur in a reasonable time. That means you have two reactants in the solid states. The lower one, you take care of that melting point, and 2/3 of that melting point is the limit normally to which you heat to raise the temperature to bring about your reaction in the solid state. Moving further, now these are the details of the Fick's law, this Fick's law, which I have mentioned to you, which controls the diffusion rate. So those of you who have studied physics in the past, they would be aware of this particular law. And as it's written here, this law, diffusion occurs in response to a concentration gradient expressed as the charge in concentration due to change in position. The local rule for the movement of flux is given by the Fick's equation that is shown on the slide, in which the flux J is proportional to diffusivity and the negative gradient of concentration. The negative sign indicates that it is positive when movement is down the gradient. That is, the negative sign cancels the negative gradient along the direction of the positive flux. The flux is driven by the negative gradient in the direction of increasing x. X is the layer formation or the product formation that is taking place in the case of when the reaction is proceeding. And this the x is used later to define the complete kinetics of this particular reaction. Now, for a solid state reaction, what are the favorable conditions that one looks for, so that without much difficulty you can conduct these reactions? It requires thorough grinding is necessary to achieve a homogeneous mixture of reactants. The reactant A and B, which are solid in nature, they need to be first mixed in a quantitative manner in the stoichiometric ratios, and then thoroughly grind it or make homogeneous mixture of these two reactants. The number of crystallites in contact may be increased by pelletizing the powder using hydraulic press. This is another route. How can you bring about more homogenization of the mixture, that is the pelletization of the powder? The reaction mixture is typically removed and regrinded to bring fresh surfaces in contact, which speeds up the reaction. Now this third step that you have seen in this slide is, this is sometime when the reaction is in process, you stop this reaction after a certain interval, cool this mixture, bring out this mixture, and then grind it so as to expose the fresh surfaces to be in contact, and this process will speed up the reaction. Although the temperature plays its role in speeding up the reaction, but by bringing more new surface contact areas, the reaction will also speed up. So this is a very important aspect, that while the reaction is on, you stop it, cool it, regrind it, and restart your reaction in order to complete it to the required level. Continuing with this thing, with the favorable conditions, reaction times are sometime in hours. These are not a reaction which can just you can start and finish it. They may take very long hours, but may take even several days to complete, or weeks, or even in certain cases they take months to complete. And with intermediate grinding, which I mentioned to you in previous slide. That means you stop the reaction in between, take out the reacting mass, again grind it, put it back and restart your reaction. Then, as I mentioned in the beginning itself, sample purity is typically examined during by powder X-ray diffraction. Now, when you do the reaction, the sample property of the reactant that is taken, you can subject it to X-ray diffraction to see its purity. The type of furnaces, because the temperatures are very high, therefore you need to have metals which can withstand those temperatures, and such substances are silicon carbide and molybdenum silicates with heating elements. So therefore they are the one which withstand these high temperatures, and you have to work with these materials in order to make your furnaces or containers to proceed with these reactions. Continuing with this, to give you more example, conversion of electrical energy into heat to a temperature of 2300 degree K. You can achieve this. For this purpose, an electric arc directed at the same sample may achieve as much as 3300 degree K. A carbon dioxide laser can be used, which can give you temperatures up to 4300 degrees C. So these are the various methods using electrical energy to reach a temperature of the 4300 degree K. Now, what are the containers, the reaction materials? What we call them, in this particular case, we call it crucibles. They must be able to withstand high temperature and sufficiently inert to the reactants, that they must not react with the reactants that we have. Common crucible materials are silica, which can be heated up to 1430 degree K, alumina to up to 2200 degree K, zirconia 2300 degrees K, magnesia 2700 degrees K, platinum melting point 2045 degree K, silver 1235 degree K, and like gold, which is about 1000 degree plus degree centigrade, can also be used for some of the reactions. So most of the things that you'll find in these containers is, which we shall see later also in example, that these are very expensive material, refractory material, which can withstand a very high temperature, because these reactions, they take place high temperatures, so the container has to be such that which can withstand and give you those temperatures. Now, having seen this, the general background, how the solid state reactions they proceed, what are their general way of doing it. Now let's move to the, as I said in the first slide, what are the general principles involved in such reactions. Now in this thing we shall see, we'll introduce these general principles, we'll talk of the reaction conditions. Now since we are going in for the reaction, we shall look into the why solid state reactions are difficult. We'll also look into their reaction rates, and we shall all look into the reaction mechanism. And the reaction mechanism of such reaction was given by the name by a scientist called Wagner, which we shall take into consideration when we talk about this. Now starting with this, let us say see the slide. This is the standard ceramic route of making polycrystalline materials in these solid state reactions. The easiest way to make any solid state material is direct reaction of their components at a high temperature. This is the most easiest way. For example is shown here is magnesium oxide plus alumina gives you magnesium aluminate. This is called a spinel, the product. This reaction occurs around 1200 to 1500 degrees centigrade. What we need in this case is, we need to grind, we need to mix the powders, reactants, and either press them into pellets and heat. So how the reactants are to be prepared in order that this reaction can take place. So this is called a standard ceramic route, and this is the example that we are going to take to follow all the general principles that are need to be elaborated to you for solid state reactions. Now, moving on to the introduction of these ceramic methods. This is the most widely used method for the preparation of polycrystalline materials or solid powders, and it's a direct reaction in the solid state of a mixture of solid starting materials. You have seen MgO plus Al2O3, magnesium oxide and alumina in the previous slide. Now these solids, they do not react together at room temperature or over normal time scale. Since they do not react at room temperature, therefore it is necessary to heat them to much higher temperatures, often 1000 to 1500 degrees centigrade, in order for the reaction to occur at an appreciable rate. Please note the word, the temperature and the appreciable rate means it should be within reasonable time the reaction could be completed. So therefore there has to be a balance between the temperature and the duration in which this particular product can be made. So for this reason, hence both thermodynamics and kinetic factors are important in such reactions. Now both the things, rate of the reaction and the rate of the kinetic factors, the diffusion of the reactant, etc., they are both governed by thermodynamics and kinetics. So therefore these two factors, they become important. What does thermodynamics do? Thermodynamic considerations show whether or not a particular reaction could occur. That means it tells you the feasibility. You determine the free energy of the reactants, and therefore you will know what is the possibility of this reaction to occur by considering the change in the free energy that are involved. That is how the thermodynamics is used, that even before you start with these reactions, you can fall back on the free energy of the reactants and establish the feasibility of such a reaction, and then come to the kinetics determine the rate at which the reaction will occur. So that's how the temperature, residence time and the rate of reaction, they are all important in the solid state reactions. Now what are the factors influencing reactions of solids? Now for this purpose, we shall take a practical case, and the practical case is MgO plus Al2 in the ratio of 1:1 to form what we call as a spinel magnesium aluminate. This is the net product that you'll get when you react magnesium oxide with alumina. And you take the mixture in 1:1 ratio, stoichiometric ratio, and the product so formed is called what is called spinel. Now what is a spinel? That is also defined for you. It's a hard glassy material occurring as an octahedral crystal of variable color and consisting chiefly of magnesium and aluminum oxides. It's very important. Both are colorless, but the product is colored material. Chemistry wise, any of class of oxides including spinel containing aluminum and another metal having the general formula magnesium metal aluminate is normally called as spinel. That's why when you react magnesium oxide and aluminum oxide, they lead to the formation of MgAl2O4. Then moving on to what are the reaction conditions for this, for the magnesium and aluminum to occur. What does thermodynamics suggest? From the free energy consideration, magnesium oxide and aluminum oxide, they should react together to form magnesium aluminate. The feasibility of the reaction is proved using the free energy. Reaction rate of this material, of this reaction, is very extremely low at normal temperature. Only above 1200 degrees centigrade, reaction does begin to occur to an extent. That means up to 1200 degrees centigrade, there is hardly any movement in the product. There is hardly any reaction rate, so therefore minimum temperature required is 1200 degrees centigrade to be heated, and that thereafter needs to be increased to complete the reaction. For complete reaction of the powder mixture to occur, it may be necessary to heat it for many hours or days at a temperature around 1500 degrees centigrade. So starting at normal temperature, they do not react. Reaction is feasible. Minimum temperature required is about 1200 degrees centigrade, at which the reaction begins, the process of diffusion starts, and in order to complete the reaction, you have to raise the temperature of the to about 1500 degrees, and it may give you at that stage the required product. Now, what are the factors that enables you to overcome the diffusion barrier? And what are these diffusion barriers? What does it mean? That the two reactants that you are using, magnesium oxide and aluminum oxide, they need to be in intimate contact for the reaction to occur. And this intimate mixture of the reactants can be obtained in several ways. That this can be assured, and this will give you a better diffusion rate in this. Number one, very small particle size reactants. That means the surface area is very large. The reactants are in the form of a very fine powder, and therefore they'll give you a better rate of diffusion. Then, in addition to this is all mechanical that you have received. You can do it chemically in certain other reaction, not for this reaction, particular reaction. Find molecular precursors that has the needed element in the correct ratio. For example, one example is which is shown with barium. To such precursors you can add, which will bring about the closer contacts with this in the reactants. In the second case also, they make a solution of needed melt metals and dry the solution without demixing the components. That's another way of ensuring that how to produce an intimate mixture of the reactants which can give you the required rate of diffusion of making the products at a lower temperature and in a given duration. So this is the first step, how to ensure the intimate mixture of reactants either through the process of grinding and mixing or through the process of use of precursors which can enable you to have the intimate contact. The second thing that you need to consider is the structural considerations. Now, structural consideration here means the crystal structures or the structural form in which the two materials are there. Now, magnesium aluminate crystal structures show, that is the final product if you look at it through X-ray diffractometer, that show similarities and differences to both MgO and Al2O3. What does it mean? That the final product that you are getting, MgAl2O4, it is similar in certain way to MgO and Al2O3, and it's also different from MgO and Al2O3. So therefore, there's a structural similarities as well as certain differences. Now, what are those? Both MgO and spinel is your magnesium aluminate, the final product, have a cubic closed packed area of oxides. That means they have a similar structures. In contrast, now this is a difference to aluminum oxide, which has distorted hexagonal closed packed area of oxides. So one has a packed area of oxide, another has distorted hexagonal area of oxides. So therefore, magnesium oxide is much closer to the spinel that you are making, whereas the aluminum oxide is much different than the spinel that you are making. Then on the alumina side, aluminum ions occupy octahedral sites in both aluminum oxide and spinel. That when the spinel is formed, the location of aluminum oxide, the Al3 plus ion it occupies the octahedral sites in the crystal and in the spinel. Whereas in the case of magnesium ions, they are octahedral in magnesium oxide but becomes a tetrahedral in the final product. So therefore there is a difference. From hexagonal to, it changes to octahedral in the case of aluminium, and magnesium changes from octahedral to tetrahedral in the case of spinel. So therefore structural similarities have to be viewed very closely to